And so the next part, we're getting to the pH. To understand the pH or how much acidic strength, we need to understand what's happening with water. The pure water is non-conductive, will not conduct electricity. And so roughly 2 out of 1 billion water molecules become ions. So this equilibrium is basically very few out of 2 billion water molecules here. You got only 2 of them becomes ions. So 2 water molecule will give you 2 H plus and 2 hydroxide ions out of 2 billion water molecules. And the actual concentration, it is in the pure water, these ions both come from water. So in pure water, these 2 concentrations will equal amount. And they both equals 10 to negative 7 mole per liter. And so 10 to negative 7 is basically 1/10 of a millionth. For every 1 liter of the water, there's 0.1 millionth or micromole of the water becomes ions. Micromole, 10 to negative 6. So it's a very, very small amount. And since in the water, these 2 concentrations so low, it's non-conductive. There are basically no free ions to conduct electricity. By the way, I think most of you notice when you take a long walk around, and then finally you see the elevator, you want to use the elevator. Did anything happen to you when your finger touched the elevator button? Anyone? Did that happen to you like occasionally? There's a zap. It feels like a very uncomfortable, almost like I've been stung by a needle. Did this happen to you guys? Push the elevator button, and then you hear a little bzz, a little noise, and then you have the tingling, very uncomfortable tingling. That is basically the water in the skin. It contains ions. Okay, remember our body has a lot of ions, has a lot of sodium ions, potassium ions. And then when we sweat, or not visibly sweat, there's a tiny amount of moisture on our skin. The skin will have ions and has water. Water dissolve ions, it become conductive. And so when you touch the elevator, your skin, the tip of the finger becomes the conductor. It allows the electron, the charge to travel. And that basically gives you the uncomfortable feeling. So basically nowadays, when I touch the elevator, if I remember, I will not use my fingertip. I will use my knuckle, because my knuckle is drier and less ions, less sweat. So that means more resistant. And so if I use my knuckle to touch the elevator button, I can feel our body will discharge. But because I'm more resistant, the electric current is much smaller, and I don't feel as much uncomfortable. And so that's all because the water, it has a very, very tiny amount of ions. Okay, because the diet that we have, we always have some sodium, in our diet. And so water become ions is reversible, and this is a chemical equilibrium. When the water forming these 2 ions is a reversible process. And if it is a reversible process, then there's a forward reaction, which is dissociation. And there's also backward reaction as a combination. When these 2 reach equilibrium, that means there'll be a fixed amount of hydrogen ions and proton ions. And these 2 multiply will give us the equilibrium constant. So the concentration of these 2 multiply will give us equilibrium constant. This equilibrium constant is in chapter 6 Chapter 6, we mentioned the chemical reaction rate, reversible reaction, chemical equilibrium, the Chaffee's principle, and all these I mentioned about equilibrium. Water ionization is a equilibrium. And the concentration these two multiply will give us a constant. And the constant, the good thing is it's fairly easy to memorize. And later we'll find an even easier way to memorize this. It's 1.00 10 to the negative 14, fairly small amount. That means that is because the water become ions very, very poorly. Most of the water molecules do not become ions. So if these two concentration multiply give us constant, that means if one of these two increase, because we add an acid or base, then the other will change backward. If one increase, the other will decrease to maintain the product of these two giving the same volume. If one increase, the other decrease. If the one decrease, the other will increase. These two multiply give us constant. So as for example, if the proton concentration increase, then the hydroxide will decrease, and vice versa. If this decrease, then the other will increase. And because we start from here, we have a way to find out if one of the concentrations is given, we can find out the others. So from this equation, if we are to solve the proton, I simply just need to divide by the hydroxide from both sides. Kw is 1.00 10 to negative 14. So if you have the hydroxide, you can find the proton concentration. Because this is a constant, same number will not change. What if you want to find the hydroxide? That would be the similar start from this equation. I divide by the H plus. You can solve hydroxide. And so that's where we, if we were given the hydroxide to find H plus, or we have the H plus to find hydroxide. It's a simple math. And for water, okay, neutral solutions means there's no extra protons which will come from the acid, or hydroxide come from the base. None of these two. The water will give you very, very small amount just by itself. Remember, every 1 billion water molecules, there are 2 of them becomes the ions. Okay, there are only 2 of them become ions. And if it's a neutral, no acid base, then these 2 will be equal. And since these 2 multiply, the H plus times hydroxide, give me 10 to the negative 14. If these 2 equal, then I can solve for the hydroxide or proton. These will equal, and these both will equal 10 to the negative 7 m, which is a very small number. So again, because the water is not a good conductor, it has almost no ions, very, very few ions. Acidic solution, if we add a compound with a proton, then this concentration will go up. If this go up, the hydroxide will decrease, because these 2 multiply give me constant. Oh, it's negative 14, not 4. And negative 14. One goes up, the other go down. It's like a seesaw. The kid play the game, seesaw. One person go up, the other person go down. Up and down, seesaw. Acidic solutions is a molecule give proton water. so that this will go up, increase, and the other will go down. And that's if you use the 10 to the negative 7 as benchmark, as a reference, as a control. This is neutral. So if a proton is more than that, that'll be acidic. When the protons are more than that, then the hydroxide will have to be less than the 10 to the negative 7 m. It's low. Neutrals, when these two equal, both equals that. One goes up, the other go down. So if this one, H plus goes up, the hydroxide go down. Basic solutions are just opposite. So for example, sodium hydroxide dissolving water. It'll bring a lot of hydroxide to the water. So we have a big surge on the hydroxide. And then same reason, because these two multiply equals constant, hydroxide increase, then the proton will have to decrease. And so if, again, we use a 10 to the negative 7 as a benchmark, as a reference, then the acidic, it'll be less than that. And hydroxide will be more than 10 to the negative 7. So acid base, we can use the 10 to the negative 7 concentration as a standard. This will be neutral. If H plus more than that, that'll be acidic. If hydroxide more than this, that'll be basic. So that'll be very easy to keep track. This is the is a very small concentration, but it's a condition no excess hydroxide or proton. And so here were some examples how to do some calculations. And we have, you will see this kind of question back and forth in our homework and quiz, online quiz. And so to decide the solutions acidic or basic, we use this compared with 10 to the negative 7. Just need to remember one. For the acidic is when the acidic, it is when the protons more than 10 to the negative 7. That will make it acidic. So any calculation, any discussion, ask about, is this solution acidic or basic? Make sure you, if you see this, that'll be acidic. If this did not happen, which means otherwise, it will be neutral or basic. So this practice, we are to solve the H plus. And so first one, we have hydroxide. Well, the hydroxide, remember hydroxide and proton, these two concentration multiply give me 10 to the negative 14. So the hydroxide, we can use the 10 to the negative 14 divided by the hydroxide will give me the proton. So use this divided by the hydroxide concentration will give me the proton. And so use my scientific calculator. I have the answer for that actually. I have the answer. Because this is 3 sig figs, 1.00, 10 to the negative 14. This one is 3 sig fig because 1.00. So finally, can only keep it to 3 sig figs. This is the answer I will get. Be careful. Even the K have no units. The KW, which is this number, very small, have no units. When you use the K to find the concentration, we need to add a unit back, even though the end there's no unit here, and this is the molarity in big M. But still, since we're solving the molar concentration, we should add a unit. The unit, it is M. Because that's what a K is based on. The K is based on the two concentration multiply. And then once again here, we can answer the next question. Is this solution acidic or basic or neutral? Acidic, just remember this one. Acidic is when you H plus more than 10 to the negative 7. If this happens, means the solution is acidic. And you can see this is 2.86 10 to the negative 7. You've got a decimal part more than 1. So this will be larger than 10 to the negative 7, which make it acidic. So if you start from hydroxide and ask about H plus, we have a way to solve. It is use Kw to solve. Use Kw to solve the H plus. Okay, next example, sodium hydroxide, 0.000250 M. This is even off. Where does H plus come from? Okay. Keep in mind, this be the strong base. We show you the alkali metals give a strong base. This is strong base. So when you have a strong base, the hydroxide concentration will equals the concentration of the compound. Hydroxide will equal this because it's complete become ions as a strong base. Once you get it here, the next we just repeat what we did here. Use the 10 to the negative 14 divided by hydroxide. Divided by the hydroxide will be 0.000250.
So 1.00 times 10 negative 14 is the formula for these three practice problems.
Basically, well, mostly you will see the last one is actually not. Last one you don't need to. Yeah. Oh. Only if your solution start with hydroxide, yes. If your solution start with hydroxide and ask you about the H plus, then yes, use the Kw divided by the hydroxide. Yeah. And so with that, I have the answer for 4 point. And again, the Kw have no units, and here we have a unit, but nevertheless, in the end, we are solving for molarity. We add units back. And you can see this number compared with 10 to the negative 7, this is smaller. So that means this is basic. And how would you know? You can see the decimal part is bigger, but remember exponents much more important. The exponent, when you have 10 raised to the power, exponent different by 1, that means it is 10 times difference. So that's why we compare the exponent first. That's just more important. Once the exponent be the same, then we compare the decimal part. So to find the hydrogen ion, we use Kw divided by hydroxide. And the last one, HCl, the strong acid. This kind of question, sodium hydroxide and HCl, how does it relate to H plus? So realize either the question will give you, we'll let you know. Sodium hydroxide should be the strong base because this is group 1A. It's group 1A elements under the lithium. Above sodium is where above the potassium. So this is sodium. Sodium hydroxide is strong base. We're using the Drano in the drain cleaner. Oh, by the way, kind of sidetrack, digress. The drain cleaner sodium hydroxide is not good for the kitchen sink. The kitchen sink, it is the clogging mainly come from the vegetables, mostly the vegetables. And the vegetables is unlike the animal or human hair. Vegetables pretty much resistant to the base, will not be dissolved by the base. So it's completely different from the human hair or animal hair or protein scale protein. The the vegetable fiber mainly is not protein. It is a sugar becomes the bigger molecules. That sugar bigger molecule better breaking down by the acid. But still, for the kitchen sink disposal, we don't want to use the strong acid. That'll corrode the pipe, corrode the disposal itself, the garbage disposal itself. And so don't use the drain cleaner or the liquid plumber for the kitchen sink. It won't work, just because it needs a different kind of reaction to break down. And for the bathroom clogging, mainly because of hair, and that you can use a strong base like sodium hydroxide or very concentrated base solutions. So anyway, back to here, we have this is strong acid. Okay. How would you know? Well, I don't really ask you to memorize this, but the question here oftentimes, just because the way we ask you, we assume the strong acid. And when you have a strong acid, then it 100% become ions. The hydronium or proton is same as proton. Okay, in this chapter we interchange all the time. Sometimes I get to kind of mix them together. They're the same. The H plus, it is just when chemists are lazy, they want to write something less. They simplify by taking the water, H2O, out of H3O. So now you have only one H left. And the charge stays. That's what happened. It's the same thing. Anyway, once you have this, then your answer, the question being answered. What is the hydrogen concentration? Realize this is strong acid. It's strong acid, then it's the same. The hydrogen ion concentration, it is 0.50, which is much, much larger than 10 to the -7, which means this is very strong acid. It's very acidic. Because when you have that compared with 7, that'll be neutral. So that's when you have a different solutions, how would you find the proton concentration? If some other question asks about hydroxide, you do the same. Because the hydroxide and a proton concentration multiplier give me 10 to the -14. Give me one, you can find the others. And so if you visually give you scale, neutral is where these two will equal amount, which equals 10 to the -7. And because these two concentration give me 10 to the -14, which means that if one goes up, the other goes down. So when we have a lot of acid, the hydroxide will be very small. If there's very few hydrogen ion, then you have a huge amount of hydroxide in the solution. Well, these are, we saw the concentrations, the concentration represent is a very small number. And so you get a 10 to the negative a whole number. Decimal part, it's okay, it's manageable. But using this way to represent concentration is kind of too much work. You have a decimal part and exponent. To make your life easier, chemists or mathematicians invented a way to make it simplify. Basically, we try to extract the power out of the concentration. So to extract the power of a number, it is through taking the logarithm. So basically, when you with the concentration proton, you take the negative log of concentration. Well, the concentration oftentimes give you 10 to the negative number, 10 to the negative power. Take a logarithm will give you a negative number. Okay, when the power is negative, the logarithm will give us a negative number. And again, we don't like to deal with negative number. So we define a system, it is we turn this whatever number into a positive by adding negative times -1 for the logarithm. By doing this, we get a number that is more manageable. It's typically between 0 and 14. Much easier than a number very small, and you have an exponent. Sometimes people get lost, get confused, and don't know how to use a calculator. By doing this, the number you get from the concentration, it will be typically between 1 and 14. More manageable. And what you get by doing this is we call it pH. The P here means the power. Okay, so basically means power of a hydrogen ion. That's what a pH means. Power of H+. That's what it means at pH. And so what exactly pH? How do you calculate? Use a neutral water 10 to negative 7 to calculate. 10 to negative 7, you take log of 10, will give you negative 7. And then you, oh, sorry, I forgot about this. How can I forget that? That's, you should keep the negative in front. Okay. Negative log will give you pH. Make sure you have the negative. Log of 10 to negative 7 give me negative 7. And then I change the sign by the front. I get a positive 7. The pH equals 7. It is a water pH, which is neutral pH. Okay. pH equals 7, that'll be neutral. Like a extremely pure water will give you 10 to negative 7, 10 to the negative 7, and pH will equal 7. Okay, when the concentration of the hydrogen higher than 10 to negative 7. When the H+ is higher than that, you take a negative log, you end up getting numbers less than 7. So acidic, even though the pH means the power of hydrogen, the smaller number actually means a more higher concentration of the H+. pH less than 7, it is actually acidic when you have this larger than 10 to positive 7. Okay, why there's flip? Why there's a larger than becomes smaller than? Because we put a negative. When you put a negative, it just simply reverse the comparison. So let's say everyone knows the 3 less than 4. Okay, if I turn negative, negative 4, negative 4, negative 3, which one's bigger? Of course, it'll reverse. And that's why here you got to reverse. When the hydrogen concentration is larger, pH actually smaller than the 7. And so for what for basic? Basically, when the concentration is less than 10 to the 7, you take a pH, it becomes actually larger than 7. Larger than 7, the solution is basic. When the H+ concentration is smaller than the neutral concentration. So that's how you find pH. We'll show you some example how to find pH. If this reaction reverse, if I have a pH, let's find out H+. If you have the pH and find the H+, so basically start from here, this equation, we have pH. We solve for the H+. Some of you learned algebra. This is actually a very good exercise. When you learn algebra and try to reverse, when you have basically y equals negative log of x, and my question asks, what is x? What is x? I think most of you probably have not learned about how to solve x. But for those of you who learned the algebra, learned the pre-calc, you might figure out, remember some skills you can do. So basically, remember 10 log of 10 A equals A. And so that means I can, with this equation, I do the same on both. And this part, okay, still there's inconvenience. There's negative here. Negative actually means inverse of x. Anyway, I will not continue, but those of you who learn the algebra, you can easily prove it. And the equation, if you have the pH to solve H+, you basically change the sign for the pH first, and then use the your calculator have a key like this. You have this key in this function in your calculator. Just use this key to easily calculate the proton concentration from pH. And so that's basically the calculation. Later, you see some homework, see some practice. We have an example here. Let's see, continue some example later, postpone. The pH scale is much easier to represent the concentration of proton, H+. And as we saw, the low pH means more acidic. Low pH actually means more acidic. High pH means more basic. And the 1 pH unit, it corresponds to 10 times difference. 10 times. Or a factor of 10. And so that's the pH scale. Difference by 1 means actually 10 times difference. By the way, the earthquake scale uses a similar scale. The earthquake, we have a Richter's scale. That is basically every 1 degrees in that earthquake degree magnitude difference, it actually means 32 times. 32 times energy difference. The normal earthquake we have in our neighborhood is about magnitude 5. Magnitude 6, the earthquake is much stronger. How much stronger? 32 times stronger. Magnitude 7, okay, magnitude 7 compared to magnitude 5, it'll be 32 square times, which is about 1,000 times more energy. And that's why the magnitude 5 earthquake is just barely shake. We feel it barely shake. But in magnitude 7 earthquake, the energy is 1,000 times bigger. The damage will be proportional. It is much stronger, the damage. And if you continue to move on magnitude 8 earthquake, that energy, it is cube of 32, which is about 30,000 times more energy. If magnitude Earth, the magnitude 8 earthquake hit Los Angeles, it pretty much levels everything because the energy is 30,000 times more energy than our barely little bit shake earthquake, like magnitude 5. The magnitude 5 earthquake, if you check the California earthquake map, it shows you happens all the time, almost every several months. You get magnitude 5 earthquake. But in that magnitude 8 earthquake, that is much more energy, more destructive. Anyway, the pH scales by every difference by 1 means 10 times difference. It increases slower than the earthquake energy difference. Anyway, the most pH, when you have a pH 0 means when the H+ equals 1 molar. This 1 molar concentration is fairly strong, but not the strongest yet. Okay. The molar is 1 mole of the acid, strong acid, in 1 liter solution. This is very mild. It's very mild, strong acid. And that pH will give me pH 0, which is very acidic. The pH 14 is most common, the strongest base. Even though the drain cleaner that we use to dissolve aluminum can, that pH is more than 14. So basically our Drano or liquid polymer pH is actually more than 14 because higher concentration than the 1. The Drano concentration is 2.5, as I mentioned before. That'll make it a very strong base. And also if you buy the works, the acidic cleaning agent from the store, and that pH is actually below 0, it's negative. It's very, very acidic. So that's about the pH scale. And how we make the pH scale, we use a pH meter. The pH meters electronically measure the voltage change by the acidity. And these are some pH we saw from our everyday life. A lot of common items we have. Start from the most acidic in this list is a 1 molar. We call it 1 molar. And it means a mole per liter. But in common words, actually, we just call it molar. It's associated with the molarity. Molarity is equals mole per liter. Anyway, these are the fairly strong, but just keep in mind, not the strongest. There's some pH even be negative. So start from that, and the 0.1 molar pH, because in here, the H plus equals 0.1. If you take a negative log of the 0.1, that'll give me -1, and you change the sign, give me +1. So 1.0, this means this solution acidity is 1/10 of this. It's a weaker acid. And our stomach acid, in our stomach acid, we have hydrochloric acid. Where does it come from? It's our body basically use table salt, and through the complicated mechanism, our body be able to move all the protons, a lot of protons, to the stomach. Our body needs this acid to break down the food. It needs the acid. And also kill the germs, kill the bacteria. Most bacteria, if we eat them, if there's not so much toxic proteins or molecules in those germs will not bother us because acid destroy those proteins, the virus or bacteria, because of acid. So we need to maintain the healthy acid level in our stomach. pH between 1 and 3, that's a fairly acidic. And then the lemons have a citric acid. Citric acid, fairly acidic. Give me pH 2, that's a very strong acid. There's one time I squeezed one of the citric fruit, the juice falls to the dirt, and the juice basically make the dirt fizzle, because citric acid can dissolve the calcium carbonate in the dirt, make a carbon dioxide gas. And there's some other soft drinks, very acidic. The sour taste make them more stimulating. And so the vinegar pH is about 3, vinegar. Okay, it's not in this, but the white vinegar pH is about 3. And then the rainwater 5.6, a little surprising because the water is supposed to be 7, simply because there are carbon dioxide gas in the air. The carbon dioxide dissolving water make the carbonic acid. And carbonic acid is weakly acidic. So that's why the tap water or just natural water, it is slightly acidic. But if there's an acid rain, because industry, human burn the coal or the other mineral ores, they produce sulfur dioxide, eventually making a very acidic rainwater. But that's the beyond our discussion. And the human blood, our blood need to maintain the very narrow pH range to be healthy. It's almost neutral, slightly, very, very slightly basic. And there are many other stuff. Basic, egg white, slightly basic. This is the one form of antacid, milk of magnesia. It is magnesium hydroxide. It's a weakly basic, fairly high, but not too high pH. And the cleaning household vinegar, ammonia is around 11. That's fairly basic. 1.0 molar sodium hydroxide, exactly 14. And the Drano is even more than 14. The drain cleaner. So those are the pH of the common substances. Okay, let's see some proxies on the pH, then we can. The pH of those solutions, basically if the question give you H+, you just simply use the negative log of the H plus to find pH. So this question gives you H plus, and that will make it easy. It's negative of log. So if you solve that, and this portion, use your calculator, that should give me about 4 point, negative 4 point, negative 4 point, 5.2. This one, you need to use your scientific calculator. Okay, I'm going to use my scientific calculator, do the negative. Log is negative 4.28. Those kind of calculations, how many sig figs, there's a rule, supposedly a rule to keep how many sig figs. But to make it simple, your pH calculations keep just 2 decimal places. Okay, for all the pH calculation in the future, keep only for the pH. Okay, only 2 decimal places in your pH calculations. Keep only 2 decimal places. And so here I round off, whatever here I round off. Final pH 4.28. So that's, if you have the H plus, you just simply just solve like that. What if answer for pH, but H plus not mentioned, then we have to think. And typically the answer is pretty straightforward. Okay, it depends on what is given. The first one, HCl, if you remember, this is strong acid. Okay, the strong acid, then that molarity, it equals H plus concentration. H plus equals this. And then you solve pH. Solve pH, this would give me finally 2 point. Okay, I don't remember the answer, but the answer key is in the PowerPoint, 2.7. I should keep the 2 decimals. Okay, let's calculate what would be the exact number. 2 point, around to 2 decimal will be 2.70. It is 2.69897. To keep 2 decimals, I keep to here, so I need to round to here. This one round up. So it becomes 2.770. So that'll be the answer for this solution. So you can see the this number is much smaller than 7. Reason because your hydronium concentration much bigger than 10 to the -7, making it fairly strongly acidic.
So the way how you got these numbers, all you have to do is just put them on the calculator, and then you would get these answers. But you have to make sure it's log.
Yeah, it's log and it's negative. Make sure you have negative.
Oh.
Negative log.
Oh.
Yeah. So these two, the first one is fairly straightforward. But second one, we have to think about, is it strong acid or weak acid? But typically we only give you strong acid. So you need to know how to calculate strong acid. So this chapter, the acid base pH, it is kind of more advanced level calculations. And you will not see the pH calculation until you do the Chem 1B. 1B, you'll be doing more work on the pH. That's the next level. And you explain more. In the book, they will explain more about pH. Okay, the last one, this is a little tricky. You have a sodium hydroxide. This formula does have H. Okay, keep in mind, the hydrogen here, it actually always goes with, stay with oxygen. This solution actually will give you hydroxide. It is strong base. The hydroxide concentration equals 0.010. Okay, it's not H plus, it's hydroxide. This is strong base. So give you strong base. then realize the hydroxide equals 0.010. And then you have hydroxide, but no hydrogen ion yet. We need to calculate. Use 10 to the negative 14 to calculate. So this is just we mentioned earlier in the examples. Use 10 to the negative 1 divided by hydroxide will give me the hydrogen ion. So use your calculator, that'll give me negative 12. Okay, 10 to the negative 14 divided by hydroxide, divided by the hydroxide, and hydroxide is 10 to the negative 2, right? That's 10 to the 2. So you would get 10 to the negative 12. And then since you have the proton, you can do the pH. pH equals 12. Keep 2 decimals will be 12.00. So take a negative log of this number, the H plus concentration that is just solved. You find a pH. So this chapter, in the middle, we have quite a few logarithm calculations to find a pH. And today we focus more on the water equilibrium, the KW. We use the KW to calculate the hydroxide or the hydronium or proton concentrations. Use this number. So today I'm supposed to start the acid base, but I think we're run out of time. And Friday I might have to catch up on the titration calculations. And because this Friday our lab believe it is about the acid base titration. And so that's, let's see what's next. pH. So these are the decimals. I did not really, in this chapter, pH and decimals, sig figs, is not the most important issue. I will not check about the sig figs as much. There's a rules. You might learn the rule in Chem 1B, but not here. Okay. Our class, the calculations, when you watch for when you do the other calculations, all the earlier calculations. By the way, the acid base is the last place where we'll have some calculations. The next one chapter, no calculations. So we're going to the end of the calculation in this chapter, in the whole class. So this chapter, the pH and the sig figs, I will not check too much on this. Be more flexible. I'll be more flexible. Just don't keep too many decimal places. Because there's no need of keeping that many. Keep 2 decimal for pH. That's sufficient for almost all the work. And we can do the reverse calculations. I mentioned there's an equation about reverse. If you have the pH, and we have an equation to do that. Okay, so that is H plus. Basically, you do the anti-log. And so if you have a pH, use this equation to calculate. pH is 3.7. So just replace the pH, substitute pH with 3.7. And your calculator will give you a very small number because this exponent is negative. You get a few decimal places. And I do have answer for that. The answer I also rounded. You might see more digits, but keep about 1 or 2 sig figs in your concentration. So 3.7 negative, and then use 10 to the, in my calculator, 10x power is the second function. It's the So I get, what my calculator get is 0.00019995. And then there are more digits. But keep only about 2 sig figs. This part can be more flexible. So there's a rule, but I don't want to get into the rule, get confused everybody. We're getting close to the end. You round to 2 or 1 sig figs. It depends on, do you want to keep a 1 or 2 sig figs? You just round. So if you round from here, then it becomes 0.0020. And there you go, you get an answer. So today's lecture, we focus more on the pH and how we do the pH or reverse pH. And here's the reverse pH. Okay, the Friday, I start a new chapter. This is our pH related to the relative strength. The high pH means very basic. And the low pH means very acidic. And the reactions. Okay, this we'll save for next time. I think today we are done for the lecture.